Okay, thank you so much, Raf. That was very nice. Very nice. All right, so I guess I should start sharing before
You've already started sharing with us, Chris.
I. All right, let's see here. Back to business. This is not.
One of my favorite quotes is from Yo-Yo Ma, who said, "Sharing is better than proving." It's a
Hmm.
really deep, quote you have to think about for a while what it means.
Oh, I like it. I feel like I've just learned that for myself again recently. Yeah. Oh, yeah, yeah. Okay, this share screen is not doing what I asked it to. Okay, let's try again. I'm going to close this. Not that talk, this talk. Okay, where do Hilbert spaces come from? Everybody sees that?
Looks good.
Great. All right. So yeah, today I think a half hour of this talk is just going to be me talking about history because I want to show you guys something that happened that I think is very interesting. So many of you maybe are aware that Weil was a student of Hilbert. And well, because Weil intersected with Schrodinger, that influenced the theory that we use today greatly. But Weil also intersected with other mathematicians. He had the knack to work in many different fields. Uh, and in particular, he intersected with this guy Cartan. And it is through the work of Cartan that I've been able to bring my own perspective to some quantum information problems, which I hope to share with you. All right. So I think a great place to start is, well, I think all of you know a Hilbert space is a vector space that has an inner product, right? And in fact, it's this inner product which is the foundation for any quantum mechanical prediction. And the inner product still today continues to inspire quantum physicists to tell this story of states and measurements being these subtly distinct things, the subtlety not appearing in classical theories. But I want to point out that even it took a while, perhaps 50 years between when the inner product was envisioned by Hilbert to when it became, it had the solid interpretation it does today. Okay, so I think a good moment in time is to remember this 1954 when Max Born himself was given the award. I believe this is a picture of him at his award ceremony. Yeah, but what Hilbert was doing originally is he was just thinking about the real line. Okay, so I think a lot of you will be familiar with this particular inner product. That is the inner product over the Hilbert space of square integrable functions on the real line. And this is the direction I want to start with. But before I talk even more technically, I'd like to tell you guys a few stories. Okay, so I think one of the most interesting ones at this point is the story about Minkowski and Hilbert. So by the time 1912 comes around, Hilbert has basically mastered every branch of mathematics that existed at his time. And from that point on, he would only think about physics problems. And while at Göttingen, he created these fantastic mathematical physics courses with Klein and Minkowski. And in fact, Max Born attended these classes. So that's an important little fact. But none of that probably would have happened if it wasn't for an event in 1890 with Minkowski. You see, Minkowski became a professor at the University of Bonn. And at the University of Bonn, he had inadequate mathematical colleagues. But Bonn also had Heinrich Hertz, who at the time was experiencing a lot of excitement verifying Maxwell's equations. Okay, so that year that Minkowski met Hertz, he actually decided not to go back to Königsberg, where he normally would go for holiday. By the way, Minkowski and Hilbert were old friends. So Minkowski would write Hilbert often. And that's what this little letter down here is Minkowski has just met Hertz, and he's telling Hilbert about what's going on. So I might as well read this, because I thought this was fun. So Minkowski writes to Hilbert, perhaps I even would have had to pass through a 10-day quarantine period before you and Horowitz would have admitted me again, mathematically pure and unapplied to your joint walks. You can imagine how delighted I was to read this recently. Oh God, everybody's quarantining themselves. So this is really important. Minkowski started to think about physics, and 20 years later, because of the ideal situation that he was in with Hilbert, mathematical physics would essentially become a thing. All right, I have another story for you guys. So over here, this little box that has Hilbert, Lee, and Klein. So maybe you're aware, well, maybe you're not aware, probably you're not aware. So 1869 is the year that Lee and Klein were doing their first postdoc in Berlin. So Klein was from a family of nobility. He was professionally trained by Plücker. Probably heard the name Plücker when you're thinking about identities between elements of a Clifford algebra. While Lee came from a family of Norwegian farmers, I believe he was the first in his family to go to university. And in fact, Lee thought he wanted to do astronomy, but in his first year of university, he had quickly found that he was gifted mathematically, and he was expedited into a postdoc at Berlin. So Lee has a reputation for the next 40 years for being quite wild. And in fact, it was because of the hard work of Klein that Lee would even have a job years later. Yeah, and that's interesting. So Klein created this whole vision called the Erlangen program while he was a professor at Leipzig. But while he was doing all of that work, he was actually in intense competition with Poincaré. And in fact, this competition became so intense that at some point Klein would have a mental breakdown. And after that, he stopped doing creative work and had invested himself completely in academic maneuvering. So he moved to Göttingen. He was the chair at Leipzig, and so he gave that position. He took care to make sure Lee got that position. And then he moved to Göttingen. And at that point, it is said that the greatest thing he did was to bring David Hilbert to Göttingen. Okay. So I just told you guys two stories that changed the world. Germany was a great time at the turn of the century, last century. All right, how long did that take? Maybe I should move on. Did you guys know that Weil actually dated Schrodinger's wife, Annemarie, while they were married? That's fun. Yeah. They met in 1921. They were both chairs of their departments at Zurich. Yeah.
I think it's important to note that everyone knew about it involved. It was not.
Right. There was no shame about it at all. Yeah, there
Yeah.
was no scandal. I think maybe the proper term is Weil was Annemarie's mister. Is that what you would say? He wasn't her mistress. He was her mister. Is that? I don't know how you would describe that.
I think they're just part of the same polycule, but I don't.
Yeah. All right. Yeah, and in 1924 is when Weil met Cartan. So 3 years after Weil had inspired Schrodinger to think about inner products. In fact, I think it was in 26 that Schrodinger actually published the Schrodinger equation. And in that same year, Schrodinger published a review article on color theory, which uses inner products to think about how, you know, every power spectrum can be written in terms of an RGB triple of numbers. So Schrodinger was thinking about inner products intensely, thanks to Weil, in ways quantum mechanically and beyond. All right. Are there any questions at this point? I hope you guys enjoyed the story time. Okay. So now,
Maybe just a comment.
yeah.
We did enjoy them.
Okay, thank you. I'm going to try to put you guys down here so I can see the titles of my slides. Okay.
Absolutely. I also just I commented that I guess you can't see the comments when you're presenting, but this is a side note. mistressship is the only word in the English language that has a triple letter combination in it. It's got 3 S's in a row.
Oh. Wait, would you spell it MISSS?
No,
Oh, I
mistressship.
see. Not consecutively. I see.
No, consecutively.
Yes.
Consecutively, but it's the other S that's tripled.
Yeah. Mistressship.
Hmm.
Yeah.
I'm
Anyway.
afraid my phonetic abilities are not good enough to dictate what you're telling me. Yeah. I'll take a look at the comments in a moment. Thank you. All right. So now another point about the real line and the inner product of first square integrable functions that you might have forgotten, which is that the inner product also. So once you have an inner product, right, you can talk about self-adjoint operators, and you can talk about unitarity, but in particular for a manifold such as the real line, there's actually a sort of very privileged self-adjoint operator, which is the Laplacian. I could be talking about multiple real lines, so I apologize. I sort of toggle back and forth between the two, multiple real lines, 3 real lines maybe. There's a privileged self-adjoint operator, which is the Laplacian, invariant under translations. But there's also the privileged unitary, which is the transformation from direct space to reciprocal space, if you want to think of it that way. And in fact, it's through these simple subtleties that the entire story of scattering theory emerges, right? Where instead of thinking of Gauss's law as doing these divergence theorems, you can think of Gauss's law as an expansion in terms of a quadratic theory. Right? That quadratic theory, again, corresponding to the structures that the inner product originally was designed to elaborate on. All right. So, and if you think about it for a while, you realize that, well, the thing that defined the inner product ultimately was this property that the measure had, that it was translation invariant. Okay? So, if you're not aware, I believe Haar was either late 1800s. I know Haar was quite a time after Helmholtz. And Helmholtz thought a lot about spaces of rigid motion. So I threw Helmholtz in here because I think his name deserves to be in there too, even though normally you would call this property of a measure Haar. Certainly Haar wasn't around by the time Hilbert was thinking about these things. But Hilbert was inspired by Helmholtz. Okay. So why am I telling you guys all about this? Oh, hello.
What is the condition that is making the Laplacian so privileged here? Not just translation invariance, right? I missed that. Why is the...
Oh, okay. So I think it is the quadratic differential operator that is self-adjoint under the Haar measure.
Okay, sure. All right, thanks.
Yeah, and I love quadratic theories. And I hope I'll convince you that you can love them beyond flat spaces. All right. Are there any other questions? Okay. So why am I talking about this original inner product? Well, because actually this way of using the inner product allows you to understand a great deal about manifolds in general. Okay, so maybe you're familiar that you have a similar kind of equality between direct and reciprocal space for the circle. And maybe you're also familiar that you have a relationship between inner products in direct and reciprocal space on the sphere. Okay. Maybe something you might not have noticed is, well, actually everything about the measure on the circle, it can be encapsulated in algebraic properties of the complex plane, and thus, the notion of residues, etc., emerges. Well, the same thing also happens for the sphere, but you have to think a little bit more about what you're doing. So right now, I just have sort of a formal expression for the measure of the sphere. I'm sort of defining it as having its invariance under rotations, and that somehow that measure is in fact uniquely defined by an object that looks very residually. You just, because it's multidimensional, you have to work it a little bit more. Okay. All right. Are there any questions here? Right now, I'm just suggestively showing you guys things. I hope you don't mind that. I will leave details of actually understanding how to calculate with these things to the papers I've written. Are there any questions?
I feel like I've lost the story a little bit, but
Sure.
only a little bit.
Okay, so the point I was making is that inner products can be used to understand manifolds. And what I was trying to do is remind you guys of things that you enjoy when it comes to inner products over square integrable functions on the real line, and then suggesting to you that actually you can do entirely the same treatments for manifolds in general, especially when you have a measure that can be defined by its invariance properties. Okay, so the first two lines are supposed to say everything that you love about Gaussians and propagators and, you know, things that you know how to calculate very well ultimately emerge out of a Haar measure, and things like spheres and circles also have Haar measures.
Chris, just to punctuate that, so it seems also that the right-hand side of those equalities are, I should be thinking of spherical harmonics or
Right.
harmonic
Oh,
functions.
thank you for pointing that out. Yeah, so I guess I should point out to you guys that, you know, when you look at these expressions, especially for the circle, there is a problem that you've already solved, right? Which is understanding the spectrum of the manifold itself, right? So in this case, I explicitly said for the circle that the spectrum is just e to the in thetas, or, you know, they're enumerated by this number that ranges over the integers. And then when I wrote the sum over L and M, I guess I was assuming that you were familiar with the structure of these, maybe you'll call them quantum numbers L and M. Okay. Yes, so the sum is representing an already solved problem. Yes. Thank you. And in fact, but you can solve that problem just from the Haar measure, just like you can define e to the ikx. Right, these spherical harmonics are defined by a privileged Laplacian, etc. Yes, yes, those are exactly the points that need to be emphasized. Thank you. Are there any other questions or comments? All right. Okay, what do we have next here? Okay, I want to make another point. So group theory as applied to physics seems to default to a particular kind of application. So I wanted to make this point in the following way. So probably if you ask any physicist why are groups useful in physics problems, they'll say, oh, because groups are a way to describe symmetries. But usually people like to emphasize that the symmetries you're talking about are the symmetries of fields, say, in a Lagrangian. Okay. So you think of all of the sort of order parameters you can put on a space-time, for example, if you're doing high energy physics. And then you turn a crank, right? Feynman has demonstrated to us that almost everything you could ever want to predict in a field theory can be perturbed from vacuum expectation values of a Gaussian problem. Yeah, so that's what I mean when I say these. Is usually symmetries are thought of as the symmetries of fields used in your theory. But what I'm trying to re-emphasize to you guys is that group theory actually has a totally different application, which is to describe spaces that have symmetries. Okay? And this is, and in particular, I'm thinking of continuous symmetries. Yeah. Okay. So I could think of a field theory on a sphere, for example. These are the kind of group applications of group theory I'm thinking of. And this isn't very popular. Yeah.
Would you say that, you know, people just think about those vanilla geometries and fancier fields on them, and you're sort of emphasizing that you can put these fields on different background geometries and.
Certainly, if you're calculating cross sections for the LHC, the manifold that you're putting all your fields on is locally flat. So, but of course, so Witten is known for thinking hard about putting field theories on a 2-sphere and a 3-sphere. You know, there's the WZW models. I think Xiaogang Wen has thought a lot about discrete analogs of the WZW model. But yeah, so field theories on curved spaces is certainly a thing you can think deeply about. But most people don't. Are there any, did that answer your question, Carol?
Yeah, exactly.
Are there any other questions? Cool. Okay, what else do I have here? Aha, so, gosh, what do I even want to say here? So these methods of Cartan, which I've sort of learned to use during my time at CQuick, have not been utilized in physics much. In fact, it's interesting how I've found a couple of books where Chern, maybe you guys are familiar with Chern, knows his topological field theory very well. Even Sheoni likes to talk about Chern numbers. Chern once wrote an introduction to a book on differential geometry, and he marveled that somehow you could get to this. So Chern was a field theorist, and he sort of admitted that he didn't understand this Cartan way of thinking about things, or at least he couldn't understand how it motivated basically the secrets of the fiber bundle that every field theorist eventually enjoys. So what I'm trying to say here is Cartan was, thinking about just what does it even mean to move through spaces, and somehow arrived at these same wonderful structures, these better ways of thinking about wave functions. Yeah, and I think one of the big reasons why Cartan's methods did not make it into physics is actually because of something that Hilbert overlooked. So there's this thing called Hilbert's fifth problem. So when Hilbert was thinking about Haar measures, he recognized that Haar measures could be calculated using the differential properties of the manifolds they describe. But he somehow didn't like that because he knew that continuity was deeper than differentiability, and that measure theory shouldn't care about being able to differentiate. So Hilbert sort of got at the deep places he wanted to go in the fashion that he did by sort of dismissing differentiability. And so he did his own thing, but eventually would create during these lectures he gave in 1900 Paris, what's called Hilbert's problems. I think there's 23 of them. And the fifth one is this, he was pretty sure, but he didn't know, probably wasn't willing to do the work at that point because, I mean, you can only do this kind of work so long before you're tired. The question was, are differentiable groups the same thing as integrable groups? And yeah, integrable groups are called topological groups, but I use the word integrable because topological, there are subtly different things that should ring in your mind than what you're probably thinking when I say topological. So integrable groups that have Haar measures. It turned out Gleason himself would be the guy who would partially resolve this problem. I don't remember the last time. Oh, Gleason's theorem is something about the foundations of quantum mechanics. I don't know Gleason's theorem, but I know the fifth problem. And so I appreciate Gleason suddenly. Okay. Is there anything else I want to say here? Oh yeah, so Cartan's method basically in the end is taking advantage of when you have an Euler decomposition. That really is the heart of his entire methodology. And eventually what's great is even when you don't have a Euler decomposition, you have locally Euler-like decompositions. And that's sort of how you get into the secrets of non-abelian gauge theories, etc. I'd love to talk to you guys about that, maybe offline. But if you look up, say, the Wessel-Witten model, so here's a field theory that gets put on a space-time, you'll notice them go on a lot about teleparallelism and how it affects renormalization group. And it took me a while to realize that teleparallelism is basically just, so all manifolds have Lie algebras, but not all manifolds have Lie algebras that are constant. And the manifolds that do have Lie algebras that are constant still have curvature, but are said to have teleparallelism. So that sort of explains why, for example, you can calculate all the harmonics of a sphere just by playing around with commutators, which is really cool. That just blows me away. Yeah. I hope some of you have appreciated that you can somehow calculate just playing with commutators all of these LM states for a system that has spherical symmetry. That's kind of amazing because these LMs are supposed to be harmonics on some entire manifold. And yet here you are diddling around with linear terms that appear in a Hamiltonian. And yet you arrive at all the LMs. Yeah, so this is called teleparallelism.
Chris, can I ask, just so I understand?
Please.
It seems you're emphasizing that playing around with these local objects, these generators, somehow holistically gives you the geometry of the full manifold. You're on something global from something local. And that's what you're saying is called teleparallelism?
Yeah, that the whole manifold is connected. And it's connected in a way that the Lie algebra at every point has it structured because of the Lie algebra at one point.
It somehow knows.
It knows because of how it's connected to itself. Yes. Great. In fact, that's what this R inverse dr is all about. Yeah. Are there any other questions? Let me get a time device. Here we are. Okay, half hour. Good. Let's see, what else do we have here? Okay, Cartan's list. So I think I think it's fair to say that the climax of Cartan's career was in his 50s, soon after he met Weil, where he finally answered this question on the top, which is when are translations, because manifolds are just sets of translations in a sense, when are translations the same as global isometries modulo local rotations? Okay. So for example, the two-sphere is such a thing, right? So, and this takes some time. So SO3, maybe you're aware, has 3 generators, call them JX, JY, and JZ. It takes time to realize that one of them is describing local rotations. So, you know, if I put a point on the North Pole, it's fixed under Z rotations, but actually Z rotations transform the space around that point. So Z transformations don't do nothing. They actually generate local rotations. And then maybe you're familiar that, well, all manifolds are going to have local translations and local rotations. But in fact, SO3 itself, you know, is 2 local translations plus 1 local rotation generator. And you can just take advantage of that. And that's one way of thinking about Euler decompositions. Of course, you know, once you figure that out, you want to ask yourself, well, when do you have the ability to do this in general? And eventually you find out that actually all such manifolds with this property are made out of a basic 27. And this is just a really wonderful thing. So why should you guys care about that? Well, I'll hope that you might care about it a little bit by appreciating that actually these 27 types of manifolds that have nice translation rotation relationships is actually the same thing as certain types of matrix diagonalizability. Okay. All right, so here is a list of physics problems that have nice solutions you might be familiar with. So random matrix theories, superfluidity, superconductivity. You might think of these problems as special kinds of matrix diagonalization. Okay. Similarly, standard singular value decompositions. But then there's many more. So even the Foucault pendulum and Thomas precession fall into taking advantage of these nice manifold properties. And also, I'm so happy to say this quantum illumination. So, you know, Raf has loved listening to me talk about this stuff for years now. And I was so happy to see it inspire him to think about quantum illumination in a group theoretic way. So that's very cool. And quantum illumination was a term that Seth Lloyd hyped up. And at some point, Carl and Raf got so exhausted at how many people were thinking about quantum illumination in a broken fashion. This SU11 structure, though, was also appreciated a long time ago by Bernie Yerke in a different context. Perhaps that also inspired Raf and Carl. All right. And actually, my favorite application of these manifolds is the falling cat. Yeah, so if you ever look up, you know, the physics of falling cats, you will not probably see this sort of symmetric space way of thinking as an answer. So the point is, you're supposed to think of a cat as a head that's an SO3 and a tail that's an SO3. And then you have this control problem, which is the cat wants to do this, but of course the cat can only do this kind of stuff. But then you can solve the time optimal control problem and see that actually the best way for the cat to do this globally is to do this. Let me do that again. I'll do this. This. Yeah. So falling cats also fall under the category of physics problems that can be solved using these special manifolds. Are there any questions? Oh, these little yellow balls are called Dingen diagrams. So it turns out all the structure, all of these circles represent SU2s, manifolds in the shape of SU2. And the way that these circles are connected to each other is describing how the whole manifold is shaped by how its SU2s are sort of weaved together.
Could I ask a question?
Carl, is that you?
Oh, well, indeed it is.
Yes, you can ask a question, please.
I'll let you see me. What is these, those with the 27 with constant curvature, what does that have to do with the aforementioned teleparallelism?
Okay, so all of these manifolds have teleparallelism, which is to say that all of their translation structure can be described by a single Lie algebra. Okay, so I feel like I need to ask you to re-ask your question if you're not satisfied with the answer I just gave you. Was the question, what is teleparallelism for each of these?
No, the question was whether, probably the question was whether these 27 Lie algebras with constant curvature are the whole deal with teleparallelism.
Yeah, so I think it's the whole deal. So as far as I understand, I see string theorists and field theorists talk about the effect of teleparallelism on the normalization group. I see that they're talking about it in the context of Wess-Zumino-Witten models. Meanwhile, differential geometers such as Helgeson, who I think still can be found at MIT, use the term parallelism to mean when all the covariant derivatives of the Riemann curvature are 0. So what I just told you was there are two very different looking communities using the word parallelizable and teleparallelism. And I think it is intentional. I don't think they're talking about different terms. But then their agendas are different, right? Field theorists want to renormalize the hell out of theories. Geometers, I don't know, it's not so obvious to me that they're all about renormalization. Does that?
Well, I will ask another question if you think you have time to answer it.
Oh, yeah, I'm happy to just talk about whatever. I'll try to race to one of the punchlines.
So, you know, an arbitrary Einstein spacetime has a local structure, which is Minkowski everywhere, that is Lorentz transformations everywhere. But there's no such thing as the global Lorentz transformation unless the space is flat. And I'm wondering to what extent these spaces of constant curvature and the teleparallelism are equivalent to saying that there is a global transformation.
Okay, sorry. So I think I've left out a crucial word then. So all of these manifolds are said to be globally Riemannian. So the Riemannian means in this.
Yeah, but I'm not worried about the Riemannian. You could think it. I mean, I'm not worried about the pseudo-Riemannian of this time. I'm just worried about whether, I'm just asking about whether the global symmetry transformation is equivalent to, the same as, sort of like constant curvature and quantum and teleparallelism.
Would you ask me one more time that last question? Just so
Is the global ability to do global transformations instead of just local transformations, is that the same thing as having constant curvature and as having
yes.
parallelism?
Yes, and that is in fact considered to be the work of Helgeson. So Cartan arrived at all of these lists with kind of a broken idea of what he was doing. He knew very well what he was doing. But in the end, to say that actually manifolds with constant Riemannian curvature are the same thing as manifolds that have global isometries. That are so known.
Yep.
Cool.
Thank you.
Fantastic. Any other questions or comments? All appreciated. Okay. Okay, I think I have one more slide and then I'll start talking about what I've done while I've been at Secret. So I want to give you another provocative fact. So this slide is titled, "What is SU2?" So I think most of you will immediately answer a particular way, which has to do with sets of 2 by 2 matrices with certain properties, right? Unit determinant and the old U dagger U equals 1. And maybe some of you have played around with that enough to realize that SU2 is in fact the same thing as a 3-sphere. And I just want to point out to you guys that in the last 15 years, because of the proof of the Poincaré conjecture, we actually have an alternative, more topological definition of what is SU2, okay, because SU2 is a 3-sphere. In other words, the Poincaré conjecture, or is now a theorem, asserts that the 3-sphere is the only compact 3D simply connected manifold. And yeah, if you're I really developed an appreciation for simply connected thinking about control problems. And when you're talking about paths that connect you to a target, and thinking about the kind of problems that make optimizing over all paths difficult, I came to really appreciate what simply connected means. And yeah, I think you guys would also like simply connected if you only spent a little time with it. Usually simply connected is described in terms of path properties. But you can also think of those paths as gradients to phase structures that you put on your manifold. And I don't know, that's another way of thinking in case you find that helpful. What else? So maybe you guys are aware that even though Perelman hit this punchline, he actually turned down the Millennium Prize. By the way, this was the only Millennium Prize ever offered up to date. And the reason why he turned it down was actually because the program to actually prove this, actually a generalization of it, was his friend's invention, his friend Hamilton. So Perelman really felt like it wasn't ethical to accept the prize when the hardest part of the work was done by his friend. He just hit the punchline. This generalization, maybe just in the spirit of classifying manifolds, is this idea that every three-dimensional manifold is basically a finite number of stitchings between 8 kinds of geometry. 8 kinds of geometry is a little bit of a generalization of the kind of things that were showing up on the list of the previous slide. Yeah. There's other things I could talk about here. You notice I have a quote from Weil in this funny picture of Coxeter. But I think I'll elaborate on that some other time, or if asked. Otherwise, I'm going to move on.
Maybe I could elaborate on it briefly.
Okay.
Jonathan Gross and I managed to get a paper published on, just published in JPhys A, about estimating a single parameter out of many. That is a Fisher approach to that. We used a very geometric approach where everything we derive in it is from pictures. And we got a lot of flack from referees who said people have done information geometry before and you need to reference all that. So we did. But then instead of heaping scorn on all that work ourselves, we quoted Chris Jackson as saying it was all algebra fever. That is, people who refuse to think geometrically and reduce everything to algebra before they even start. And that's published now. So Chris Jackson is out there as the author of the phrase algebra fever.
Yeah. It's interesting to think how in 1946, this quote from Weil even demonstrates that. Okay, I'll just read the quote. It says, "My vindication for having proceeded in a much more conservative manner than our young generation of algebraists would probably deem desirable is a wish not to sacrifice the past." So you see, once people realized you could calculate, a boatload of harmonics just using algebraic properties, people didn't want to think about derivatives anymore. And so even Weil himself was fighting, or you had to explain himself to this new attitude that mathematicians had, which I thought was funny. It's not often you see an authority feel like they need to explain why they're not doing it the way everybody else is doing it. That's cute. Thank you, Carl, for bringing that up. Other questions? Coxeter has a couple of books on projective spaces that do all of their proofs using picture drawing. And I haven't studied any of them, but if I ever had the time, boy, would I like to spend it with those books. Maybe some of you are familiar that projective spaces are a great way of thinking about quantum mechanical problems. Okay. All right, so now with the times. How much time do I have? Speaking of time, I have 10 minutes. Okay. I'll try to
well,
keep it.
Chris, we can go a little over that because we normally afford our speakers, say, an hour talking with an extra half hour of discussions throughout, and we've been interrupting you. So,
okay.
Yeah.
Well, in that case, I'm going to leave it to you, Raph, to cut me off.
Okay, I can do that.
I'll just keep going. I apologize to any of you who... I'll make sure to hit the multi-qubit tomography slide in the next 10 minutes in case you're here for that reason. Okay. Where are we? Okay, so when I came to Albuquerque, it's 2017, soon after I came, I had to finish up a couple of papers I was writing with Van Enck on how you would even know if you had misbehaving state preparation and measurement devices when they're both misbehaving. After I finished that up, both Ivan and Carl asked me to pay attention to their most senior students at the time. So both of them had given these students these incredibly large projects. And yeah, it was really hard for these students to wrap it into something that they felt good about when they left. But also they had learned so much that they were ripe with, someone to have a new perspective to come in and appreciate all of their hard labors. So I feel very grateful. This has really set the stage for my entire career, the work that these two students have done. And yeah, for that I'm truly grateful. So what are these two projects? So this guy on the left, Ivan's student, is Azad. He was thinking about measuring many-body spin correlations. I think even our Dropbox folder was titled Measuring Many-Body Correlations. But by the time they had brought this project to my attention, Ivan was doing a bunch of these gestures. And they were thinking about this spin coherent state measurement, the so-called spin coherent state measurement. And they were pretty sure that they had found a way to implement it. Now, the spin coherent state measurement is something people became interested in '95. But I think by the time 2001 came around, there were all kinds of papers written saying, oh, the spin coherent state measurement is not something you could do practically because of all kinds of arguments based on the way they were thinking about things. But it turns out that if you know how to think about continuous measurement in just the right way, suddenly the spin coherent measurement doesn't look so intimidating. Meanwhile, Ninat, this guy, Carl's student, was thinking about fermion simulability, in particular, demonstrating problems are simulable by how you would solve them with a phase space correspondence, continuous phase space correspondence. Okay. Maybe just to say what's on this slide. So under Azad, I have this, Krauss operators somehow always go to things that look like this, where these things on the left and right are spin coherent states. This little figure is a description of the isotropic measurement, where I have this pudding of spins that are being collectively coupled to in their X, Y, and Z components by a Stokes interaction, I believe, where these red lines I'm suggesting lasers that have polarizations that are coupling and then being detected. And then you have these readouts that I'm representing by Wiener processes. On the right, we have the Wigner function of a fermionic vacuum state in the phase space correspondence, where the phase space is the space of BCS superconducting states. It's a funny kind of phase space to think about, but it's sort of the only continuous phase space you can think about because fermions are high maintenance. Maybe that's a way to put them. All of these funny squiggly lines are actually harmonics for parafermionic systems. And I just enjoy them so much that I want to show them to you guys. And the reason I have this New Mexico symbol with these 4 extra lines in the corner is because it turns out that there is everything you want to know about fermionic systems in 4 modes comes from, remember I was showing you guys these Dinkin diagrams earlier. And those Dinkin diagrams describe these sort of angles that are in your space that determine the structure of everything else. And for 4 fermionic modes, you have these 4-fold degeneracies in certain directions. And then you have these other kinds of operators. So these lines are supposed to be arrangements of operators that displace in the manifold of BCS coherent states. And when I saw the 4-fold degeneracies in the edges like this, it just made me think of the New Mexico sun. So I couldn't help myself. There it is. Okay, I think I said everything about what's on this slide. Oh, Chris Ferry was a postdoc that I think was the main inspiration for this project. And then Carlos Riofrio and Amir Kalev inspired this project with Azad. Any other comments or questions? So this was, I guess I've said things that I've done with these projects as well, but I now want to focus on the points I want to make before I leave the center. Okay, so I've been writing furiously for basically ever since the pandemic happened, it's been kind of a blessing for me to suddenly have the devoted time to just think about writing. Very grateful for that. And I think there are 2 points that I want to make to all of you through writing. And I'm going to do my best to explain to you what to expect in these 2 things I'm about to write. So when we realize that the spin coherent state measurement is implemented by an isotropic measurement, we had a particular way of showing that, which had to do with taking derivatives of the singular value decomposition. And that was great. However, I found it not satisfying because of another perspective I've always had. So I don't know if you guys are familiar with, how do I want to say this? If you've ever done stochastic calculus deeply, you might appreciate that there's always 3 ways to do stochastic calculus. There's the Fokker-Planck equation or diffusion equation way of thinking about random processes. There's the stochastic equation way of thinking about random processes. And there's the path integral way of thinking about random processes. So what we did here was the stochastic equation way back in 2018. And it really haunted me that I could not do it the other 2 ways as well. It sort of demonstrated to me just how much I didn't quite understand everything about what we had just done. So I'm happy to tell you guys, thanks to the attention of Carl actually, I was able to figure out how to do this problem in those 2 other ways as well. And that's what I'd like to share with you guys. Yeah, in the best way I can. So in the end, I think the point of this slide is that the isotropic measurement can be partitioned in terms of operators that take their value in a manifold, a particular manifold. And once you get there, then basically Bob's your uncle. And the analog of Gaussian diffusion for the isotropic measurement is Fokker-Planck equations that look like this, where this important z function is in fact what it is based on these Dinkin diagrams. That's fun. In other words, these diagrams are telling you what the set of R pluses is. I think Raf even told me recently he was very excited about polyhedra and sums over polyhedral reflections. And I told him, oh yeah, I've been thinking about those too. And that's where they are, in case you were curious about that. Okay, and I'll talk about how this has to do with multi-qubit tomography soon. This other thing I want to tell you guys about is basically how Cartan's list translates to a whole bunch of problems you can solve explicitly in time-optimal unitary control. So I think in the words of Michael Nielsen, so the thing that's hard about time-optimal control in general is actually performing the optimization over all paths. Okay, so thanks to teleparallelism, probably I'll have to work out how true that is. I mean, all of these manifolds have teleparallelism, so probably thanks to teleparallelism, it's actually not hard to do the global optimization for these problems. And so in the end, these problems degenerate to this minimization problem, where these thetas and phis that are being minimized over are again, have their structure as described by the corresponding Dinkin diagrams. So perhaps it'll be useful for people to realize that there are a whole bunch of second easiest time-optimal control problems that might sort of help them navigate through much more complicated problems. That's always my hope. And one of the problems I'll be happy to explain in this paper is the falling cat. And so this figure is sort of me making a joke, which is that, you know, if the cat was globally symmetric, it would be able to do these things. But lucky for the cat, the time optimal solution doesn't require such dramatic contortions. So in fact, having a spine that's barely flexible is good enough. So, and that's probably on purpose, right? I mean, being able to perform a time optimal solution is definitely going to help you survive. And so maybe that's part of why cats are the way they are.
So Chris?
Yeah. Hello.
So in the abstract for your talk, the thing that piqued my interest the most was this final sentence where you said we can do scalable complete tomography for multi-qubits. Because I'm thinking,
right.
n qubits, you're going to have exponentially many coefficients. How could you possibly do that in a scalable way? And so I was just wondering, is this the only slide you're going to use to address that topic, or are you planning on talking more about that?
Yeah, let me run up to it now, and then I'll run backwards as questions arise, because I did just promise you guys I would hit that point in 10 minutes, and I didn't, so I apologize. Okay, so here is a slide devoted to this point. Okay, so maybe you're aware that I can have a, okay, how do I want to say this? Let's start with the standard argument of why multi-qubit systems don't have scalable complete tomography. So the standard argument is, well, given any Hilbert space of dimension D, the measurements you normally think of will only give you D numbers. And so you would have to actually do D such measurements in order to get enough numbers to zero in on the D squared numbers you need to specify a density matrix, say. Okay. So those D numbers, though, come from strong measurements, right? Every time I do a strong measurement, then I get a distribution over, you know, at most D different outcomes. But you can think of doing, instead, a continuous measurement. So the continuous measurement literally is to just continuously measure isotropically the 3M1 local observables. That is the continuous isotropic measurement. And it performs this this coherent measurement, okay, where the POVM elements are projectors onto, well, these sort of spin half coherent states per qubit. Okay. And once you do that, well, actually you can do all kinds of predictions if you stay in the phase space correspondence of these M copies of a two-sphere. Let me try to move this so I can see the bottom. In particular, you might be interested in K-local expectation values. So I included this little thing on the bottom right that, well, K-local expectation values are just products of Y1Ms for the corresponding dimensions that they care about. So this is the scalable complete tomography for multi-qubit systems. Scalable because you only have to measure 3M observables, in fact, easy observables, one local Pauli's, but you have to measure them isotropically and continuously. Okay.
So if you have M qubits and you're trying to do tomography on them, how long do you have to wait to know the parameters describing that state to say some number of bits of precision? I mean, is that time scale polynomial or exponentially with that? I mean, you could be hiding it that way.
Yeah, so so in fact, it turns out that the coherent state measurement is implemented exponentially in time. Yeah, so did I have a little, oh no. Yeah, so this collapse in general is exponential in time. The POVM elements of the isotropic measurement become projectors onto coherent states in exponential time.
But that's also the optimal, right?
What is optimal?
Isn't this protocol something the optimal?
Oh, so that's a different problem. Okay, good.
Oh,
so,
sorry.
Well, it's okay. I sort of ignored that. So the original motivation of this problem had to do with if I had a whole bunch of qubits that were prepared in the same way, then there is another kind of spin coherent state measurement which measures that unknown direction optimally. But that's not what this is. Okay, so maybe I tried to emphasize that by leaving only one qubit per black area, while the optimal stuff had to do with having identically prepared qubits all being collectively coupled to. So this is not that. I know it looks a lot the same because it's still multiple qubits. It's just not collectively coupling.
So maybe I'll ask my question another way. Is this efficient in the dimension of the Hilbert space and not the number of qubits? Because fundamentally, I just don't understand how you can even write down an exponential amount of information in a polynomial amount of time. Just merely the act of writing it down seems like it would take too long. So
Right.
I think I'm missing something somewhere.
Right. I think, and maybe I'm also missing it, and for the following reason. So how is the information actually organized in a sense, right? So in this phase space, there are sort of high frequency variations and low frequency variations, or low wave number. How do you say that? There's, these this Cartesian product of M2 spheres has a bunch of harmonics, right, that describe its details. And the question is, to what precision do you know, say, the expectation value of a k local term, right? I think is precisely where inefficiency comes in, right? That you probably do have to do more work, wait a little bit longer, the higher the k is in a k local term you want to predict.
Maybe I can ask a related question, because to maybe make a related point to this. Is this POVM informationally complete on the space that's 2 to the n dimensional? If I wanted to, ask, which state in my tensor product space is this? Are the outcomes to this POVM informationally complete on that space?
Right on.
Right. But I'd do this measurement and I'd get one outcome ultimately.
Right.
And so that's not going to be, unlike the original motivation, as you said, in relation to the Massar and Popescu optimal problem, is that you had n qubits all in the same pure state specified by a block vector. And you wanted to say, what's the optimal POVM I should do given n copies of that,
right,
to deduce what that direction is? And the answer is, do a spin coherent state POVM, and whatever outcome you get, that determines the direction.
Mm-hmm.
But this is not the same. Doing this POVM is not going to allow you to deduce 2 to the n numbers, even if it's a pure state.
Right. Okay, so I think the point you're making is preparing a bunch of copies is also going to be a lot of work. Yeah, and I do agree that the amount of work that you have to do in making copies is going to be just as hard as in standard tomography. The only part that scales better is the
well, I guess the question is, I'm given a many body state of n qubits.
Okay.
And it's prepared, I can even be generous and say it's prepared in a pure state.
Mm-hmm.
It's some hard, in the full Hilbert space. I want to then do tomography to determine what that state is. Well, I'm going to have many copies of that many body state to do it. Right? So this is going to give me one outcome on that many, but I'd have to do it on many, many, many ensembles to ultimately, but this is telling me that there is a more generalized formulation to do multi-qubit, to do this particular POVM, which is more general than the spin coherent POBM that we worked on together. Is that a correct statement?
Yeah. So, the point of this measurement is to do complete tomography, not single shot guessing.
Right.
That's an important point. And it's true that I don't think this is going to solve all our problems because indeed something is hard. But I think the point I'm trying to tell you guys is the part that isn't hard is that, you can just isotropically measure 3M observables. And that's somehow much nicer than the protocol standard tomography suggests you would have to do.
I wonder whether, I was just thinking whether this is a path forward to the problem that we originally were trying to solve, which was...
Exactly. It is. Because
it is, exactly. So, yeah, so we need to do that.
Yeah. I'm so glad that you had the sense also.
Yeah.
Andrew, do you feel like you got the information you needed?
Yeah, I think still there's this exponential effort needed, a number of copies needed to get information on all the different coefficients. Any one measurement only gives you part of that. And I think you're saying just that you can make each of the measurements you do simpler than the sort of standard way of doing things, so that they're not as difficult as you might think.
Yeah. So I don't think they get harder, but I don't think all those copies and orders of observables, sources of difficulty get harder. I don't think those get harder. I think those are just as hard. Yeah.
Okay. Cool. Thanks, Ivan, too.
Thank you, Ivan. All right. Okay. I think, so one other point maybe I want to make is this whole work I've done on how to analyze isotropic measurements has inspired me greatly, and I hope maybe it can inspire you, because the isotropic measurement really is the most basic kind of continuous measurement you can think about. And it's basic enough that I can give you these wonderful analytic solutions. So it immediately suggests the following vision to me, which is, well, okay, so if field theorists love that you can solve Gaussian problems, and then because you can solve Gaussian problems, you can perturb to your heart's content any other problem that's close to Gaussian. Well, actually, you can do the same thing for any kind of measurement that's close to the isotropic measurement. And who knows what kind of stuff you could learn about measurement just doing perturbation theory around this most basic of continuous measurements. Okay. In this case, the propagator is a little more complicated because of this z factor, because of the curvature of the space that everything is propagating in. And you're very much going to care about that curvature because the whole manifold, in a sense, is explored before you get these projectors. Yeah. And I just love the idea of, measurement theory propagators. Yeah. So that's what I find exciting about this. Another thing is, so these path integrals that come into the way I've analyzed the isotropic measurement are sort of inside out, in the sense that what you're integrating over is not virtual paths, but literal measurement records. So that's cool. Normally you think about path integrals as sums over virtual paths, but actually you can use path integrals to talk about sums over measurement records too. And yeah, propagate and perturb to their heart's content. Maybe somebody will care about that someday, who knows?
That's first of all, that's really cool.
Yeah.
So you say actual paths, do you mean actual measurement records or different possible measurement records?
It depends on if you want to think of it in a Boltzmann way or a Gibbs way. Right? So yeah, you pick your interpretation. Do you think of a DW as the DW, you just didn't know what it was and that's why we're doing all this math? Or are you thinking of having sampled a bunch of DWs, right? So the first is the Boltzmann interpretation, the second is the Gibbs interpretation, right? So like when you're talking about a gas, for example, right, it actually doesn't matter if you're talking about an unknown molecule in a box or if you're talking about a gajillion molecules that are not interacting in a box, right? So same thing goes here. You can, and maybe that goes to the point that Ivan was making, that yeah, you could think about doing this measurement in single shot, or you could think about doing this measurement a whole bunch of times to do tomography. I guess that would be the analogy of the Boltzmann and the Gibbs interpretation. Either you did this a whole bunch and now you've got a bunch of stuff to look at and they're distributed the way they are. Or what you're witnessing is actually typical according to the statistics of your ignorance. Either there's one or there's many. One. Did that answer your
Could
question?
I make a comment?
Carl?
Could I make a comment on
Just a moment. Yeah, just a moment.
Go
Tula,
ahead.
did I answer your question?
No, I wanted to make a so you
Yeah,
hadn't finished and then ask me to comment.
Oh, right. So Carl, go right ahead.
So, you know, these measurement records, they're exactly like what's called unraveling a master equation. You can think of that as actual measurements and actual records that determine how the density operator is evolving. Or you can think of them as just a tool to think about what underlies the preparation of some density operator. The new thing here is this is not master equations. This is equations for the Krauss operators themselves. So you're unraveling in some sense, the diffusion equation satisfied by the Krauss operators. And that's a new thing.
Yay. Yeah,
What does that mean, Carl? I mean, I understand unraveling, these trajectories, this trajectory concept for states, but what's the notion of a trajectory for Krauss operators? Are you thinking of some like Heisenberg representation picture or something like that? What's going on?
Maybe this one.
Chris, maybe you could answer that because you probably have some equations there that say exactly what it is.
Yes, so here you have it. Okay, so the main important part is, maybe I'll back up a little more. Okay, so here is a Krauss operator you're probably familiar with. It's the Krauss operator you get from coupling a Gaussian pointer state to a observable X. The outcome of that meter state is dW. Okay, I've just written it in a certain way that I like. Okay. And so then the isotropic measurement is you just let this X be X, Y, and Z, say, observables, or whatever are the linear observables in your theory. Okay, so, and then the question is how to think about the behavior of these Krauss operators as a function of the measurement record. Okay. So there are three ways, as in any good stochastic model, there are three ways to think about how these Krauss operators evolve. Okay, so in this case, so now what I've done is I've bookkept. What's great about the isotropic measurement is that the quadratic generators that come from that Gaussian pointer basically go away. In which case now all you have to do is think about products like this. Right? And so these are the things that we're talking about having trajectories, are the Krauss operators themselves for every measurement record. Okay. Yeah, and so you get great, submanifold closure properties. You can talk about, all of the things you love to talk about when you do stochastic analysis. You can think of a distribution, which is over Krauss operators, which is a sum over all measurement records that give you such a Krauss operator. You can ask, how does that diffuse? And the point of what I'll be publishing soon is you can solve this, and that's great. And you can also think of it in a stochastic differential equation way. But we're talking about Krauss operators as a function of the measurement record.
Yeah, I guess I'm just used to maybe this more Schrodinger picture type thing when I think about trajectories, where these Krauss operators act on a state, and you get, a differential of the state, the density matrix, say, it does have these dWs on it, but it's, you think of the dWs as acting on the state. They came from Krauss operators, if you like, from this picture, but then when you actually get to the differential equation, you think of the dWs as being related to this measurement record, and so you think about unraveling trajectories of the state. And so here, yes, formally, I guess we can write the Krauss operators as functions of these infinitesimals still, the stochastic infinitesimals, but I'm just having a hard time wrapping my head around what it means for those to be trajectories, unless I'm thinking in some Heisenberg type picture where I'm thinking the operators is evolving or something like that instead.
Yeah, Yes.
Maybe I can add a comment to it, where we were originally thinking about it. When you do a continuous measurement, well, you're performing some POVM. The POVM you might think about as all the different POVM outcomes are related to the measurement record. But if you have a measurement model for that POVM, then there's a Krauss way you can think about it in terms of Krauss operators.
Sure.
And then those operators are evolving as a function of the measurement record. So the actual POVM you get at the end of the thing depends on the whole measurement record. So it's not a typical thing. No one ever has talked about this until we did. That's why
And this is not just the Heisenberg picture, though, by saying, well, the changes in the measurement record changing, the operator.
It's what's happening to the measurement operator itself. So you can think about it, you have some unitary that couples the ancilla to the system. And then, you do some measurement and that gives you, on the ancilla, that gives you a Krauss operator. But then that evolves in time, as opposed to think about it as a one-shot deal.
Okay.
Chris, could I make a comment?
Yeah.
Krauss operators are inherently a Schrodinger picture. And this is more like the path integral formulation of a green function, but at the level of states as operators and measurements that underlie the way the Krauss operators are evolving in time. But it's all Schrodinger picture.
That's right. But about the measurement, which is different than, Schrodinger, Heisenberg uses about the unitary. This is about the measurement.
Could you think about it just as a quantum trajectory for the measurement device because you're doing a measurement that could be adaptive? Or is that an oversimplification?
Want to add adaptivity?
That's a different story.
Adaptivity in here included? Because I mean,
No. This is a non-adaptive measurement. You could include adaptivity, but that's not the problem I'm solving. And in fact, if you added a little bit of adaptivity, I would suggest you do a nice perturbative approach to, yeah.
If it's not adaptive, why does the measurement you're doing at a later time depend on the measurement you're doing at a previous time?
It doesn't. You are measuring the same observables continuously, regardless of what the outcome
Right.
is.
Okay.
Before we get too deep here, could I ask that we wrap up in 5 minutes?
Okay. Yeah. Are there any other burning points or questions before I wrap up? Okay, so where am I headed next? So maybe you guys are aware, I was scheduled to move to Sydney at the end of March. And guess what happened? Well, COVID happened. Luckily, because of the sort of other things I had up my sleeve. So the original plan was, Chris Ferry had a postdoc. It would have only lasted until May 2021. So I was trying to get another fellowship so that I could stay in Sydney longer, and maybe even ultimately move to Australia. That was the plan. And so the Sydney Quantum Academy showed up and I applied for that and that went very well. But then the pandemic started happening. The Academy decided they weren't gonna hire any non-resident non-citizens. The gates closed. Oh my God. Luckily, on the SQA interview committee was Mick Bremner. And soon after my interview, Mohan asked him if he knew of any people who were interested in differential geometry. And so he thought of me. And yeah, that interview went well. And I will be starting working with him in January. So that was incredibly dramatic and been incredibly fortunate for me. Yeah, I really look forward to it. Yeah. Okay. So I really want to thank all of you. My time at CQuake has been very nice. It's also been dramatic. But in the end, I guess I am leaving with a better sense of myself. And what more could you ask for? Right? So I particularly want to thank Carl, Elizabeth, and the postdocs, and Gloria for their personal relationships with me. I feel like I've been, I don't know, I would almost say this is the most insecure period of my life because, it's taking me a long time to accomplish the things I set out to. But somehow with all of these personal relationships, I think I'm going to make it. And that's very valuable. It's been very nice working with all of the students here. These are the ones who are still around, I believe, last I checked. But of course, I've been touched by a lot more students than just these, including Gopi, Zad, Nat, etc. So I look forward to seeing you guys around. I do. Yeah. All right. So if there's anything that you take away from this talk, I hope it's the following things. First of all, history is great. It's important. It's amazing how much you can see the people in the techniques that we use today. I certainly learned so much about math by learning about the people who made the math. I also pointed out that isotropic measurements are, or I'm telling you and then asking you to read my papers later, I'm asserting that isotropic measurements are really the most basic kind of continuous measurement you could think about. And once you know how to solve that problem, well, you actually have a program to understand very many continuous measurements. So I have this dream of creating a relatively coherent theory of how to analyze continuous measurements based on this most basic kind of measurement. We've got 2 papers coming. Carl has been spending so much attention on this coherent state measurement paper, and it really is going to have a quality of writing that it would not have been without his attention. So I had to put his picture here because he's been keeping me sane during this whole pandemic. And I hope you guys will benefit from the fruits of all that labor as well, because the papers will be well written. I think most of all, hopefully you guys will always remember me as someone who really likes manifolds. All right, so with that, I'd like to thank you for your attention.
Thank you, Chris. Well, that was very valuable, very deep, and yeah, we really liked it. So I'm going to make Chris the host in case he wants to hang around if you have any further questions, but the official seminar is over and I'm going to stop recording.